Hello class. Today we're going to be talking about the quadratic formula. Mainly I want to really emphasize how we derive. Where does the quadratic formula come from? We've seen it before, I'm sure, but we want to derive it and really understand how to get the quadratic formula. We'll see how we use the quadratic formula to solve any quadratic equation. And then we're going to look at the quadratic formula and kind of see what it tells us about the type of solution that the quadratic equation might have. So far, this is what we've talked about. We can solve quadratic equations graphically, algebraically, by using square roots, or by factoring, but sometimes it's not in the right form. Sometimes we can't factor it. Sometimes it's not in the right form so that we can use the square root method. And so then we learned about how we can complete the square in order then to use the square root method of solving quadratics. Now, completing the square will always work. And from completing the square, we actually use that to come up with the famous quadratic formula. So let's start deriving that now. The key concept is we derive the quadratic formula by completing the square. Since completing the square works all the time, we're going to use that. And now we're going to take a generic kind of equation, ax squared plus bx plus c equals 0. And we're going to try to complete the square and solve for x. So let's divide by a first, because we don't like completing the square when there's an a term there. So we'll divide both sides of the equation by a. Okay, so we have this. Now let's complete the square. We're going to take b over a, divide it by 2, and square it. So by doing so, we've now turned the left-hand side here into a perfect square trinomial. Of course, we have to add it to both sides of the equation to keep our equation balanced. But let's turn this into a perfect square. Okay, now we have a nice perfect square on the left-hand side, but on the right-hand side, we have kind of a messy looking thing. We have two numbers, two fractions. Let's add them together. Now, whenever we add fractions, we need to have a common denominator. Well, if you notice here, our common denominator here is 4a squared, because we have 2a, all of that squared. So to get a common denominator, I'm going to multiply the bottom here by 4a in order to get 4a squared, and then I'm going to multiply the numerator by the same thing. So 4a. So now, let's see what it looks like now. Now I have a nice nice term here, same denominator. So I can now add them up together, and I'm going to write it as b squared minus 4ac. And now you can see the quadratic formula taking shape. Okay, now I'm going to take the square root of both sides. So, the idea here was that, by completing the square, I get a perfect square, which allows me to take the square root of both sides. So that's the nice step right here. And you notice when I do that, you see what happens, that I took the square root, and upon doing that, immediately I get a plus or minus. Plus or minus the square root of this entire piece. Now, the bottom is already a perfect square, so I could actually deal with that by just saying, well, the square root of 2a quantity squared is just 2a. And I can't do anything with the top, the numerator. That just remains, and I'm stuck with that. Final step is I'm going to subtract away b over 2a from both sides, and I get the famous quadratic formula. So, the quadratic formula always works, just like completing the square always works. And we have this formula that we can use to solve any quadratic equation. So let's look at one example. In this case, I have a quadratic equation, but it is not in the right form. I need to have an equals 0. So you notice in the previous page here, I started with something like this, and I need to have it equal 0 in order to say, this is my solution. So first off, let's just kind of manipulate such that I do have equals 0. Then I have my A, my B, and my C, which I can plug into my quadratic equation. And when I do that, I get my answer of 5 plus or minus root 97 all divided by 6. Okay. Go ahead, try it on these, and I will show the answer in 3, 2, 1. Okay. Now, I want to kind of bring some understanding that we can see from the quadratic formula. These are the solutions to this equation here, when y is equal to 0. So, our possible solutions, notice that in, say, the case where we have the square root of a positive number. So, if the inside here is positive, we have the square root of it, so it's a plus or minus a square root of a positive number. I'm going to have two real solutions. For example, plus or minus square root of 5. Now, in the case that what's inside here is exactly 0, I have plus or minus 0, which is really, I can just cross out the whole thing. I only have one solution. When this is 0, literally this can be completely crossed out. Then finally, I have a case when this term inside here is negative, so that's going to generate, when I take the square root, it's going to generate a complex, an imaginary. So it's kind of like plus or minus negative 5. When the inside is negative, I have two imaginary solutions, a plus version and a minus version. Now, we call this a b squared minus 4ac. We call it the discriminant because it describes the solution. If it's positive, we have two real solutions. If it's 0, we have one real solution. If it's negative, we have two imaginary solutions. So graphically, what it means is this. I have a function here, and it's a parabola. If I graph the parabola and it intersects the x-axis, when I have two real solutions, it will intersect the axis in two places. Okay. Now, in the case where the discriminant is 0, I have one real solution, and graphically what it is that we have the parabola, which is this graph here, but it just touches exactly the vertex, touches the x-axis. So I have only one point where the y value is 0. So I have only one solution to this being equal to 0. And then finally, we have a case where there are no solutions, because this is a parabola. And if I graph this and it does not touch the y is equal to 0 point, that means there is never a real solution for which this equation is equal to 0. Again, it never touches the y is equal to 0 line. So there's no intersection, there's no real solution, although there are two imaginary solutions. Okay, what else can we kind of see from this equation? If I kind of rewrite it like this, this might look, or should look, hopefully looks a little familiar to us. When we were graphing previously, we found that this was actually the x-coordinate of the vertex. So let's look at what that looks like graphically. Here's our parabola. This is the parabola of any sort of quadratic equation. We know previously that the x-coordinate, the line of symmetry, is where x is equal to minus b over 2a. That's the x-coordinate of our vertex, and that's this part of our quadratic. And so then we have this plus or minus piece right here. And so what that means is that from this point here, when we subtract away, we get one of our solutions, and when we add, we get our other solution. So the distance here between the x-axis point right here, where x is negative b over 2a, and our solution is actually this piece right here. So I think that's just kind of an interesting way of understanding the quadratic equation with respect to a parabola and its graph. Okay, so go ahead and use the discriminant to figure out what type of solutions there are here. I'll show the answers in 3, 2, 1. Okay, that's the lesson for today. Have a good day.